In section 6.3, we're going to introduce the concept of the scalar product or dot product. Our goals here are to use that mathematical operation and also be able to apply the dot product to the work equation and solve some work problems. So let's recall the equation for work. Remember we said that work is equal to F delta R times the cosine of theta. What is interesting about this is that it is oftentimes convenient to express this as a scalar product or as a dot product. So let's take a look at what the dot product actually is. A dot B is an operation that can be done with vectors. Just like multiplication or division is an operation that can be done with numbers, the dot product, or that big fat dot in the middle, is an operation that can be done with vectors. When you perform this operation, A dot B is equal to the magnitude of A multiplied by the magnitude of B, and then multiplied by the cosine of the angle between the two vectors. So theta is that angle between vectors A and B. So would A and B have to have the same units in order to perform this operation? That answer is no, they do not. Just like with multiplication, if you were to multiply two numbers together, they wouldn't have to have the same units in order to multiply. It's the same kind of thing with the dot product. You can simply multiply those units together. So since we know that work is F delta R cosine theta, then really this just becomes a dot product between F and delta R. So oftentimes you will see work defined as the dot product of F dotted with delta R. Some of the mathematical properties that hold for this particular operation is the commutative property, so A dot B is the exact same thing as B dot A, and also the distributive property. A dotted with B plus C could simply distribute that through so that you have A dot B plus an A dot C. Now what if A and B are perpendicular? If this is vector A and this is vector B, and they were perpendicular, this would now be a right angle between them, or a 90-degree angle. So what is the cosine of 90 degrees? Well, the cosine of 90 is a 0. So if you had these two things perpendicular, that dot product is going to be a 0. Now what if they were parallel? A and B going in the exact same direction. Now the angle between them is 0 degrees. The cosine of 0 is just a 1. And so really this entire cosine theta piece just becomes a 1, and we see that A dot B is simply going to be the magnitude of A multiplied by the magnitude of B. And what if there was 180 degrees between them? Vector A pointing one way, vector B pointing the other way. Now your angle is 180 degrees, and that would simply give you a negative 1. So A dot B would be the negative of the magnitude of A multiplied by the magnitude of B. So what does this look like with unit vectors? Here's what we need to understand. That if A and B are parallel, such as anything that's both going in the I-hat direction or both going in a J or a K, that we realize that we just get that 1 for the cosine of the angle between them. So dotting an I with an I or a J with a J or a K with a K would all be something that would get you some sort of value in the end. Whereas if you dotted two things that were perpendicular, such as the I-hat and J-hat axes, the I-hat and K-hat, or the J-hat and K-hat axes, all those axes would be at 90-degree angles to each other, meaning that you would get a 0 for the dot product between them. Here's where unit vector notation becomes kind of nice, because if we have two vectors A and B, and we could simply write them as some AX times an I-hat plus AY times a J-hat plus AZ times a K-hat, we could do the exact same thing with vector B and recognize that when you dot these two vectors together, it's really only the pieces that match up that would create some sort of a value. Basically, an I and an I would get you some sort of a value. So if you take A dot B and you put the I-hat pieces together, the J-hat pieces together, and the K-hat pieces together, you can in fact write these as unit vector notation and get a solution relatively easily. Let's look at one example of this and try this out. So let's say that you have two vectors A and B. A is 2 I-hat plus 3 J-hat, and B is negative I-hat plus 2 J-hat. And we want to dot these two vectors. So we are looking for the dot product of A and B. Dotting these two vectors is simply taking the A vector and dotting it with the B vector. So when we dot these two things together, we can take the 2 I hat and dot it with the negative I hat, where again we would multiply the two magnitudes, which is 2 and negative 1, giving you a negative 2, and then the cosine of the angle between them. Since they're both in the I hat direction, the angle between them is 0 degrees, and the cosine of 0 is just a 1. So ultimately we just end up with negative 2. Now we could also take the 2 I hat and dot it with the 2 j hat. But remember, when you have an I hat and a j hat, those two are perpendicular to each other. And when you have the angle being 90 degrees, the cosine of that angle is 0. So when you take A and B and multiply by the cosine of the angle between them, you end up with just a 0. Now we could take the 3j and the negative I hat. Again, a j and an I would be at 90 degrees from each other, and the cosine of that would give you the 0. And finally, you could take the 3j hat and dot it with the 2j hat. Again, multiply those two magnitudes together, so the 3 times the 2 gives you a 6, and the j hat dotted with a j hat would be the cosine of 0 degrees, or a 1. Now, when you add these two things together, the negative 2 and the 6, you get an answer of 4. As it turns out, when you're working with the dot product takes two vectors, and in the end, when you dot them, your solution is simply going to be a scalar. So our answer is just simply 4. There is no direction, there is no i's and j's, it's just the scalar of 4. And that's why the dot product is often called a scalar product, because when you dot the two vectors together, your answer turns out to be a scalar without any direction, just a magnitude. Now let's look at the second part of the question where they're asking for the angle theta between these two vectors. Now, since we know that A dot B is equal to the magnitude of A multiplied by the magnitude of B times the cosine of the angle between them, and we know that this is equal to 4, we could do a little bit of work and simply plug in the magnitudes of A and B in order to have theta become our only variable that we're looking for. So let's come off to the side here and find the magnitudes of vectors A and B. This was vector A. If we wanted to find the magnitude of that vector, we know that this vector is going 2 units in the I hat direction and 3 in the j hat direction. So if we simply wanted to find the magnitude of this, we could use a Pythagorean theorem where the magnitude of A would be equal to the square root of 2 squared plus 3 squared. Or A is equal to the square root of 13. Now the magnitude of the B vector, B is going to be a vector that goes in the negative I hat direction for a magnitude of 1, and the j hat direction for a magnitude of 2. So the magnitude of this resultant vector, again using the Pythagorean theorem, would be the square root of 1 squared plus the square root of 2 squared. So B is now equal to the square root of 5. What we can now do is simply plug these values in. A is the square root of 13. B is the square root of 5. Theta is now my variable that I'm looking for, and I know that A dot B is equal to 4 based off of my unit vector work that I did over here. When I plug these things in and simplify a bit, I get the cosine of the angle equal to 4 divided by the square root of 13 times the square root of 5. If you take a second and pause the video, you can plug those numbers into your calculator, and you would get that value to be about 0.496. Now solving for theta by taking the inverse cosine of both sides, I can now see that my angle is just over a 60-degree angle between vectors A and B. Notice how we were able to find a few things simply by knowing the unit vector notation for each of these two vectors that we were looking to dot. We will do more of these examples in class, so come ready with questions.